Pronk slides.
Perhaps more importantly, you can go back along the slides too.
That's right. Oh, that's right. Okay, all right, well, let's get started. It's great to have Dorette Pronk here talking about doubly lax colimits of double categories with applications. So the floor is yours. Thanks, Dorette.
Okay, well, thank you, David and Tim, for inviting me to speak. And although I would have loved to be in California at this point, it's still really nice to have a chance to talk with people and talk about the work I've been doing. And so this is joint work with Martin Schildbroek, who's here today as well, and Martia Baye. Martin is postdoc at Dalhousie, and Martia is at the University of Ottawa. So our work came from a question that Martia was actually asking us: is would double categories be used to find further homotopy invariants for spaces with a group action? I must say that's the part of the project that we still haven't completely understood and completed, but it led to a nice discussion about what should doubly lax colimits be for double categories. And so that's what we will talk about today. And we are making good progress towards Martia's question. We're not entirely there yet. So a double category is an internal category in CAT. So we have a category C0 and a category C1, a source and targets, functors, and then of course also all the other functors that I didn't give there, but the composition functor from the pullback to C1 and unit functor going from C0 to C1. But then hidden in that, there are four classes of special objects, so to say. There's the objects of C0 and the arrows of C0 that will give us the vertical arrows of what we will call the vertical arrows of the double category. And then there are the horizontal arrows, which are the objects of C1. They get a source and a target via these functors S and T. And then there are the double cells, which are the arrows of C1. They get a source and a target horizontally by taking S and T of them. Then those targets are then vertical arrows. And they also have a source and target internally in C1. And that source and target give me then their two horizontal arrows, which I think of as their vertical source and target. So here is the picture. So we have an alpha and its horizontal target. So the S of alpha is the U and the T of alpha is V. And then internally it has F and F primed as its source and target. Good, then let's look at a couple of examples. My examples are primarily made so that I can use them later. So they are kind of showing you how you can make double categories out of two categories or categories for that matter. So if we have a two category, then there is the double category of quintets that was already introduced by Charles Erisman, and where the double cells are the two cells from the original two category, and both the horizontal and the vertical arrows are simply the arrows from the original two category. So an alpha here just means that I had a two cell originally from VF to GU. And normally we cannot compose horizontal arrows and vertical arrows in the double category. But so in this case, the quintets give us a very special kind of double category where there's additional structure available. And of course, when I write this, it's only just to remind for myself where alpha was coming from. So if we may not want to put all the arrows everywhere, we can also decide to just put the arrows from the two category in the horizontal direction. Then we get what we usually call H of C. And in that case, all the cells are globular in the sense that the vertical parts are just identities. And then, of course, similarly, we can make a vertical double category out of a two category where we put all the arrows from the to category in the vertical direction and only use horizontal identities. Okay, then now the category of double categories has objects, double categories, obviously, arrows, double functors. Those are functors that preserve all that structure that I just gave you. And then, for today, it will be strict, although there is a pseudo version, but for right now, we'll just do the strict version. And two cells can canonically come in two flavors. We could make what we call vertical transformations, and they require us to assign to every object of the domain double category a vertical arrow, and then also a double cell for every horizontal arrow. So these always get kind of a flavor of being lax in the sense as you would think if this was ordinary two category. And horizontal transformations can be, so, and by the way, these have to, of course, be functorial in the horizontal direction. If I have an H composed with K, then gamma H composed with gamma K would have to be the gamma of H composed with K. And they need to be natural in the vertical direction. We also have horizontal transformations. In that case, you assign a horizontal arrow to every object and a cell to every vertical arrow. And this needs to be functorial in the vertical direction in that case and natural in the horizontal direction. Now, modifications can be then given as a next level of cells. We could call them the three cells. And modifications are given by a family of double cells. So not just horizontal arrows, vertical arrows, but double cells. The double cells are indexed by the objects of the domain double category. And so in particular, we see here that the hom between two double categories is itself a double category. So, but what we don't have, what we would really have liked to have, would have made our life completely different if we had had a double cat itself as a double category. Like, you know, two cat is itself a two category. You can also give it more structure, but you can at least call it a two category if you want to. And cat, we can call a category if you want to. But double cat, we cannot call a double category. And so, but it is enriched in double categories, as I had just indicated. And we can turn it into a two category by just taking only the vertical or the horizontal transformations. So that is a standard thing that has often been done. And when limits have been studied in double cat, we have usually looked at them as if we were working with double cat V or double cat H. So either the vertical transformations or the horizontal transformations. And then we can take the typical lax colimits or limits. And so that has led to horizontal limits and vertical limits for double categories. And the problem with that is just that you only get to really play with one part of the arrows and not with all of them. And so our question was, can we somehow incorporate both? So the first thing we have to do is to say, well, what kind of diagrams do we want? Well, we would like to have a diagram that is indexed by a double category. So that is new because so far, the fact that double cat itself is not a double category has stopped us from doing that. But we decided to say, no, we will just work with double cat and adjust it so that we can map from D into it. And so let's just see, if we just set low dimensional, objects of D have to go to double categories. Horizontal and vertical arrows will both have to be mapped to double functors because there's only one type of arrow in double cat. However, now we get to the two-dimensional level and we have a choice because double cat itself is now down to having just, so D is down to having just the double cells, one flavor, but double cat just got its two flavors, the horizontal and the vertical transformations. For today, we choose the vertical ones. Just have to make a choice. And So an indexing functor for us is then going to be a functor, a double functor from D to the quintets of double cat V. So we have, it looks like thrown out a lot of the horizontal structure by doing that, but we'll see in a moment that we can regain that once we start talking about the transformations between these functors. So the indexing double functors defined that way will also be called vertical double functors from D into double cat. So we don't have to keep writing this Q double cat V. So whenever you see this type of arrow, what we really mean is a double functor into Q double cat V. Okay, good. So as I just said, we might be worried that we have just lost the horizontal transformations and the modifications, and we might also have lost our ability to distinguish between horizontal and vertical arrows in the indexing category. And the answer is no, we will regain that by an appropriate definition of doubly lax transformation. So here we go. The way we define our transformations is similar to the way that Benabou defined them for bicategories. And he did that in terms of the cylinder bicategory. And so we start here by constructing what we call the vertical cylinder double category, because again, you could make a similar kind of construction by starting with the horizontal arrows and cells instead of what we are going to be doing. This cylinder double category will come with two vertical double functors. Remember, those are double functors into Q double cat V, but we don't say that the whole time. So we have a domain and a codomain for that. So the cylinders themselves are a real double category, and so they can map with a vertical double functor into double cat. And a doubly lax transformation is then given by a double functor from D into the cylinder double category. So these kind of transformations are only defined for vertical functors into double cats at this point. And then the usual thing is required that we have the D0 of alpha is F and D1 of alpha is G. So, okay, so let's look first at the double category of vertical cylinders. So the objects are double functors, and I will be denoting them by arrows pointing down, just because of the way that the whole construction is going to come in a moment. The vertical arrows are squares with a vertical transformation in them. And since we want to go from F to F bar, the transformation will be going from VF to F bar U. Horizontal arrows, similar ideas, they're squares again, but now with a horizontal transformation in similar fashion. So now a double cell here is then, so we have those horizontal and vertical transformations. So they have already built the outside of our cube. So our cylinders are today cubes, really, and topologically the same. And we need to just have a top and a bottom for them. So those are two vertical cells. And so a double cell consists of two vertical cells and a modification to fill the cube. And so we see that here, the alpha for the top, a beta for the bottom. One sec. So alpha for the top, beta for the bottom, and then the sigma that will connect the pieces. And yeah, it's a matter of checking that everybody fits together. So I like the picture on the right to think about, but of course, if you really want to think about it as a modification with horizontal and vertical cells, then the picture here on the left tells you how they fit together to put the modification in there. And the red part here, I think that is this is the codomain, that's the red here, and then the blue part here is the original domain there. Okay, So then, so now the vertical double functors are simply take the top, take the bottom from the cylinder, and a doubly lax transformation is done indeed, is now given by a double functor from D into this double category I just described to you. By the way, composition, horizontal and vertical, is given by putting cylinders in the two horizontal directions together. It also has a vertical composition that can be used to compose our doubly lax transformations. Won't talk about that for the rest today, but so there's more structure here. So what does a doubly lax transformation look like? Well, for each double cell, I am going to need to give you, first of all, for each object here, A, I need to give you a double functor. For each horizontal arrow, I will be giving you a horizontal transformation that sits here. And, oh, wait, actually it was the one over there. If I take the F prime will give the one over here. And then the U and the V will give me vertical transformations here. And then I finally need to give you then an additional transformation, vertical transformation for alpha that will go for the top and one for the bottom, and a modification theta alpha. And I have that, I think, on the next slide. Yes. Sorry, the F alpha, the top and the bottom are already given. My apologies. F alpha and G alpha gives the top and the bottom. So the only thing that alpha still needs to do is to put the modifications in there together with the sides. So the top is completely given by F, bottom by G, and then the sides and the modification in the middle are given by alpha. So theta, sorry. So F. So theta gives the sides and the modification. And the theta alpha is the modification part specifically. Okay, so let's look now a little bit more careful at the structure of our doubly lax transformations. They are now double functors. So between double functors, we have horizontal transformations, vertical transformations, and modifications. So we have a whole double category sitting there. So they are the objects of a double category that we will call hom DL for doubly lax. And it's a sub-double category of what we would usually call double cats from D to cylinders. So remember, double cat was enriched in itself. So that's where we see that. This is what's going to be important to get the universal property for our colimit. Okay, quick. You might be now like, okay, we have been diving deep into double categories. Let's for a moment look at a part of the world that we perhaps know better, like two categories, and see if I bring this back to two categories, what kind of things fit in here in this package. So we can, if we have two functors, we can apply Q, the quartet construction or the quintet construction, depending what we want to do. I think quartet here, yes. To the home categories of the two category at the codomain. So I'm looking here at this situation. I have two categories, A and B. We have two functors, F and G, and an alpha transformation between them. I can apply Q to the home categories of B and thereby obtain a double cat enriched category QB. Then that allows us to view lax transformations between two functors as a special case of our new doubly lax transformations by starting in QA, taking QF and QG and by looking carefully, I won't go into too much detail right now. If this Q hat B, if I bring that back, it is actually QB V. That is just going to be. So we can see QF. This can be viewed as Q of B as well, with taking the vertical part. If you then restrict, so first of all, this would just give us the general Lax transformations. Nice, okay, so at least we generalize something we knew. But what's even nicer is that we can now decide to not put all the cells in both directions when we do the Q to the hom categories of B. I could decide to only take certain cells as the horizontal part and take perhaps all cells for the vertical part, but only certain cells for the horizontal part. And that will allow us to give, for instance, pseudo transformations or transformations with any other kind of special cells that we want to use for the naturality squares. And if we want to also perhaps restrict for which arrows we want special cells, then we get the sigma transformations that Martin has worked on with Eduardo de Boek and others. And so we see that all those types of transformations can show up as special cases of our new doubly lax transformations. As usual, double categories can kind of incorporate most trouble that two categories can give us. Let's say it that way. Okay, so now let's take our doubly lax transformations and use them to define cocones, doubly lax cocones for a vertical double functor. So now we can finally start looking at our indexing functor and say, okay, what is a cocone for this diagram? And so what we then need is a doubly lax transformation from F to delta E, which is the constant vertical double functor, and of its value E. And then there is now, I will now write lax cocone LC for, remember, we could make this double category of doubly lax transformations with all the transformations between them, because doubly lax transformations were given as double functors. So we get here a double category, and this is then the Lax colimit of F. If for every other potential cone I could come up with, I have, so I take double L, this is the one, delta L is the one that we're going to define. Delta L is the doubly lax colimit if for any other E, there is an isomorphism of double categories between just taking the double functors between L and E, bits, transformations and modifications, and the doubly lax cones as defined above, which were also given in terms of, here we are, this hom. Okay, so this is a full sub double category of another hom category. So this, we want this to be an isomorphism of double categories, just like we had in the past isomorphisms or equivalences of two categories or categories for definitions of colimits. And our claim today is that we can represent this doubly lax colimit using a double version of the Grothendieck construction. So, or a double category of elements, if you like. And it's defined as follows. On objects, so remember we start out with a vertical double functor. So for every object C in the double category D, I look at FC, I have another double category, I can take an object there. So objects in our category of elements will be C, axis. Then the vertical arrows will become, again, a pair of vertical arrows, a vertical arrow in D together with the vertical arrow in the F of the codomain of the original arrow. So we have the arrow from C to C primed. We have done an arrow in FC primed that has to go from FU of X to x primed, where these were the chosen objects. Horizontal arrows, same idea. So so far, this is just repeating the usual Grothendieck construction in the horizontal direction and the vertical direction. Double cells are also fairly straightforward, but require just a little bit more thought. So what we get now is, so we have written a diagram with a frame, at least that we recognize now from what we know from before. But now what is a double cell here? Well, a double cell is of course given first of all by an alpha on the first coordinate. So this is just a cell alpha in the indexing category D. And then in the code, so in the second coordinates, we now have to start putting all the information together in pretty much the only way you can do it. So it's clear that we have the lambda going from FVY to Y primed. We have the phi primed clearly going from FF primed X primed to Y primed. Then we start working our way up and we see that FF primed of rho, so rho itself was going, of course, from FUX to X primed, but FF primed of rho will then go between the two images. And on the top, the FV phi is kind of constructed the same way. And then finally, we recognize that actually F alpha X, F alpha is a vertical transformation. Remember, here's where it actually shows up that we chose the vertical direction to do things, to start out. And so F alpha X fits there. And then our second coordinate needs to be a double cell that fills this up. Okay. So these can be composed. All of that is in our paper, which we hope to get up on the archive in a couple of weeks. We're almost done. So what I just want to say here is that one of the things we've been working on now, besides looking at its colimit properties, which are very fun and nice, we've also been looking already at what does this give us for fibrations of double categories. And from what we've seen so far is that the notion is going to be a different one from the street vibration. So it's not just an internal vibration. That can be made into something nice too, but this particular construction leads to a different notion. And what's crucial here is the fact that, and also crucial for the colimit, by the way, is the fact that our horizontal arrows can be factored, as one knows, into a vertical arrow with a Cartesian arrow. Let's think Cartesian, and vertical, by the way, that is vertical in the vibration sense, not in the double category sense. Sorry, I just realized this can be confusing. There's too many times the word vertical here. But we have the same kind of factorization on the arrows, but also a nice factorization on the double cells, which helps to show that our colimit, that this is indeed going to be the colimit, because once you then start writing out your correspondence, you need that. So I'm not going to give the whole Lax co-cone. I'll just say it is defined in precisely the way that you would expect based on how the traditional colimit goes, the traditional Grothendieck construction. And our composition by lambda does give the ISO of double categories that we need. So this is the doubly lax co-cone. And furthermore, also in the interest of finding the vibration properties and everything else, we get that this functor also extends to a functor of double categories, the double cat category, sorry, be careful. They're from taking the vertical transformation, sorry, the vertical double functors from D to double cat with the doubly lax transformations between them. And remember now, once we have data as doubly lax transformations as our arrows, then we can make them into the HOMs into double categories. We saw that before. So this double cat category can then be mapped to double cat over D, which is the Grothendieck over D with the canonical projection. And that functor, so gives, and by the way, you extend that functor by just using the colimit property. Colimits give us a universal property that allows you to turn that into a functor. And this gives us locally an isomorphism of double categories. And this is again, for those who are familiar with Grothendieck constructions and vibrations and so on, a familiar result, and kind of the result that lets you do everything around the Grothendieck construction. And so we're planning to use this further as well. So basically giving it as locally at least equivalent to the slice. Okay, so let's look at a couple of applications. First of all, we want to make the connection with the Grothendieck construction given by Bakovic and Buckley as the Grothendieck construction for two categories or bicategories. And I will just do two cat today. So for a two category and a two functor, we want to make that into a double index functor as follows. We first take just the functor itself and then compose with V to end up in double cat V. So by the way, here we have a couple of choices. We could take Q, we could take V, we could take H. Doing different things will give different results, and I'm going to explore a couple of them with you. So if we take the composition with V, we end up in double cat V. Now the important part was that I wanted to use V to get here. Actually, no, this is fine. Yeah, no, it's the next step here. The point is now that I also want to have a V on at the beginning. So I will start then out by taking the V of this functor. And that gets it then from VA to V double cat V. Well, strictly speaking, we wanted our double functors, vertical double functors to end in Q double cat V. So just take the inclusion. That's fine. And so if we apply the Grothendieck construction here, we get this here. Now, turns out, once you check out the details, this is just the vertical inclusion of the two category of the Grothendieck construction into double cat. And furthermore, this functor V from two cat into double cat V induces a two isomorphism of three categories. So this both two cat and double cat V can be viewed as three categories, of course, with the modifications. And V induces an isomorphism onto the image, and hence the colimits should be the same on both sides. So we get that the this colimit here, well, since this is being mapped to the colimit over on this side, this here itself is the lax tricolimit of F in two cat. So we end up with a nice colimit result for Buckley's and Bakovic's construction. It's not entirely surprising if you remember that Grothendieck originally introduced his construction with giving it as a vibration, but also giving the exercise that it is a colimit. And but it's nice to see how that works out and exactly which colimit do you get. By the way, if you want the pseudo colimit, you need to take some fractions of this thing with respect to Cartesian arrows, but that's the topic for another day. Okay, now we could also go in a different direction. We could more go horizontal. And in order to prepare you for that, let's look for a moment at categories of elements. So first of all, the easiest one, the one that you teach your students when you teach the first year category theory course, or first category theory course, not first year, but then if we have a functor from A into Z, we can take the category of elements, and it has the usual one, objects A, X with X in FA and the arrows as expected. Since we are going into sets, we have an equality there rather than an arrow. And then you can see that its universal property can be translated via the adjunction between pi naught and discrete to get that the colimit of f in Z is pi naught of the elements of df. And actually, this is often an exercise that I will give to my students towards the end of the term. And we can actually apply the same paradigm one level higher. And if we start out with a functor to go from A into cat, so now A is a 2 category here, then I can, instead of the adjunction between D and pi naught, I will take now the vertical inclusion. It is kind of the thing like D, because horizontally I'm going to get my identities. So it's the kind of the horizontally discrete embedding. And then what is the pi naught that goes with that? Well, take the horizontal equivalence classes. So this is the horizontal pi naught. Wait, I'll just do it a bit this way. Horizontal. So that means that I identify objects if there are horizontal arrows between them. And I will identify and so on, you know. And I identify vertical arrows if there are cells between them. Well, actually, just do alpha and so on. So this is just a horizontal quotient. And it follows then from our main theorem that if I take pi naught of HA with Q of V after F, then I get the strict 2 categorical colimit of F. So when we did the V, when we had the VA here, oops, sorry, we had the VA here, and of course no pi naught in that case, we were getting the Lax colimit. Taking pi naught with the H gives us the 2 categorical, strict 2 categorical colimit. And by the way, this elements construction was introduced by Paré in 1989, sorry, at a meeting in Bangor. And so here is the construction. He used at that time to study 2 limits and 2 colimits and weighted colimits and so on. There's a couple of nice results on those slides. And unfortunately, I don't think this has, at least not been printed by Paré himself in any officially published paper. So if others know of another place to find it, otherwise I think that's finally Bob needs to get a paper out with this in it. But it's, so it's a nice construction so for instance, we see here that what really happens is that instead of saying that lambda has to be equal to the composition of the components with of F alpha with the image of rho, we have this double cell structure and so on. So there's more to be said about that, but not for now. Just to say, this actually gives us a way of seeing that too as a colimit. The third one is one that occurred just recently in a paper by David Jas-Meyers. And so this one is a little more complicated, and I can't make it into kind of like a nice little package, but so we can see David's construction of the read products as a special case of our construction. What we do is, again, you start out with a functor in this case from category into cat, and we compose that with Q to end up in double cat V, and then we take right after that 2 first and flip a horizontal flip to end up to have the arrows going in different opposite direction. And the reason for that is then that with this way, when we now do Q of the whole thing, we get a chance to have things flipped in one direction compared to the other one. And so if you take Q of this whole thing, then we have, of course, now an indexing functor, a double indexing functor from QA to Q double cat V. And this is giving us precisely the read product as David introduced it. Just to quickly, we took his pictures from his work on the archive, and so his cells of this shape correspond to these cells. This was the second coordinate for the double cells in our construction. Now notice his commute, because in his case we were working with cat here, so there were no non-trivial 2 cells there, so phi would become an identity in this case here. And let's see. Okay, I want to say a little bit about what our original plan of our reason for starting to study this, which was the Tondi Construction for a fundamental groupoid. So I just want to give a little bit of background, like what is that construction? So this is for a space X. I just realized I didn't put it in, but I can write it now. So if we have a space X and a group G acting on it, the idea is that I want to look at all the subgroups of G, closed subgroups, if the group is topological. So all closed subgroups, and then I want to look at the fundamental groupoid of the fixed points of that subgroup H. So these are the fixed, X to the H is the fixed points under the action of H. And so in that way, I construct basically a functor from OG, which I will describe to you in a second, to groupoids. So I'm sending every subgroup G, which is going to be represented as its quotient in G mod H. Sorry, the quotient G mod H in the category OG that I'm describing in a sec, to pi of X to the H. And the idea is that I want to glue those single groupoids, now just groupoids. I want to glue those groupoids over the, I want to use OG as my indexing category, and I want to find a colimit, but I want to take the lax colimit. And which means that I will leave the length of groupoids, by the way, but no problem, topologists will still call it a groupoid, even though it isn't one. Because OG itself is not a groupoid. So when I'm indexing over something, it's not a groupoid. So we're going to be leaving something behind. So the objects of OG, so I'm now looking at OG, objects are, as I said already, the closed subgroups of G. I'm thinking of those as basically the orbit types of what kind of shapes can the orbits of G have when I let G act on a space. And those are always of one of those shapes, that it's always G mod a closed subgroup. Can just think about it for a moment. You need to see which part of the group keeps that point fixed, the points in a particular orbit. Because then once the group keeps one of the points fixed, and all its conjugates will keep the other points fixed. And so then you see what the shape should be. And so these are the shapes of the orbits, and the arrows between them should then be equivariant maps of the form G mod K1 to G mod K2. And they are actually generated by projections. Like if K2 contains K1, I can just project down. But I could also, of course, always conjugate by an element in G. And so basically all arrows in OG are obtained by these projections and the conjugations. And usually when we write down the arrows, we even think of like, okay, I've chosen my projection and I just need to write down which conjugation I now need to use on top of it. In any case, these maps can also be viewed as points in a space, G mod K1, K2, but take the K1 fixed points in there. And if you do that way, then you can see that the two cells need to be homotopy classes of paths in that space. So it's really a topological category that has been turned into a two category. But they always use the two category. I've never seen them actually using the full topological category. It might be another interesting thing to do sometime. So as I said already, then we have this as our indexing category originally, and then take the fundamental groupoids on the pieces of the space and glue them. So the plan for us is now to upgrade OG to a double category, and the plan there is to use paths in the in G as the vertical arrows, and look for a sensible way to put double cells in there, and then pi needs to be extended a bit, of course. So here's a bit more about that. So in principle, the paths in the group can now start to play more of a role. So what we would like to see with our fundamental groupoid in the end is to see how we can create kind of an direct or kind of an action of one of the groupoids on the other, or a semi-direct product of groupoids. That's how I like to think about that. And so we're still working out on some of the details. I'd hope to have that done by today, but that's teaching got in the way, let's say that way.
Your timing seems perfect, but you asked me to give you a 5-minute
thank you.
interruption. So okay.
Yeah, I think I precisely have 5 minutes left. Thank you. So we have done a couple of other projects that we have started on, or are hoping to start on soon. One is to extend this to double pseudo indexing functors. On the one hand, it's kind of intimidating to have to put the cells in everywhere. It's not that hard to understand what they should be doing. It's just a matter of like, okay, how do you write this up in a way that is not going to become incredibly technical? And on the other hand, we have a couple of examples in mind where it would be nice to have that worked out, and also to be able to make more connections with the two categories with pseudo functors and so on. So there's work to be done there. That's will come. The last one, and also in terms of the last one, this is actually needed. So because we would like to get an correspondence, as in the classical case, between a suitable version of vibrations between double categories and indexing functors from a double category into double cat as defined today. And again, so for the strict case is working out quite nicely, except I think for the full correspondence, we may have to make sure that everything works precisely, you have to go to pseudo functors. So there's some work to be done there. And that was the last slide. Thank you for your attention, and I'm happy to get questions and comments.
Okay, great. So everyone can unmute yourself and clap. There is also claps in the chat there. So let's open it up for questions. Anyone who wants to can just unmute or raise your hand and I'll call on someone. I had a quick question. I had a kind of mathy question, and I'm not sure. Well, I guess so. So there's a duality between the working horizontally and working vertically. You could have right?
Yeah.
Do you have a good way of saying how that duality kind of maps through the entire talk, like what you would see if you just watched that duality just move through the whole talk? What kind of what it would look like? Is it just a matter of every single time you see a V, you turn it? I mean, I get, but there's nothing really interesting at all. And okay.
Not at this point, because we're not doing pseudo. So
Yeah.
At the moment that you go pseudo, then you usually end up with your double category being pseudo in one direction and then strict in the other direction. And then you break your symmetry with that. And so that's where
I meant to more ask, like, is there some like relationship between those two duals that aren't just one is a dual of the other? They seem, and in general, there's
so.
no,
I don't.
okay.
I think here was simply like, okay, you have to, if you start with horizontal, you have to do the horizontal cylinders, and you need to just, really literally, it's a matter of switching horizontal and vertical.
Yeah. Okay. So not the other question was, I don't think there's any other questions yet. So I just had this thought that for the pseudo double indexing functors stuff, it's one of the first times I thought to myself, I bet this would be easier with an automated proof assistant. It's like,
ooh, that sounds like a plan.
It kind of seemed like if you could get what you already did into an automated, into a proof assistant, that like the next step might actually be easier than on paper. It was the first, so just a thought.
That sounds like a very interesting idea, because as I said, I mean, to me, it feels like there's nothing like, I don't mind doing hard work if there's something interesting to be sorted out. But if it's just a matter of like, okay, write out the details of what you believe to be true, and you expect you even know how it is true. So just don't surprise me, please. Then
that's what it feels like. Yeah.
Yes. So that would indeed. So maybe I should talk to one of our students who is working with ACDA at the moment.
Maybe. Okay, it looks like Jeff has a question. Do you want to unmute?
Yeah, gotcha. Thanks for the talk, Dorette. It was a lot of fun. I really enjoyed it.
Thank you.
I was just wondering, when you were talking about the Tondi construction and having a group acting on spaces, how gnarly are those groups or spaces? Like, are they all Hausdorff at least, or are they like awful?
I didn't say anything about that today. Typically, we assume these things to be very nice. I mean,
Okay.
if you're generally at least Hausdorff, and sometimes even manifolds and stuff. But for me, they don't have to be manifolds. I'm happy with Hausdorff spaces.
Okay.
If you really want to do nasty stuff, then we might have to be more careful. But so I think the setting where Tondi looked at this and created this thing was for Hausdorff spaces, I think, if I remember correctly.
The fact that
and also the groups are Hausdorff groups.
The fact that you had closed subgroups as your point stabilizers, does that presuppose Hausdorff?
Yes.
In the bad spaces, they might not be closed.
No. Then you have to start looking at. So then if you have bad spaces, I think you have to. Your OG has to change too in that case, and I don't know whether people have worked on that at all.
Thank you. That's an interesting thing to look at, actually.
Great. Brandon, do you have a question?
First of all, thank you for this talk. I really enjoyed it. So this is a little bit vague, but if you're taking functors from, say, a one category into double cat, I would think there are maybe, we have maybe 3 different notions of Lax functors. You could have like horizontal in some sense, vertical in some sense, and squarish, perhaps.
Yes.
Do your double functors, in the case of a double category arising as, say, commutative squares in a category of a one category, do you think that recovers all of these, or maybe like vertical and squares?
I think we get all of it depending on which composition you take, or is that not what you meant? I'm just looking for a second, because I'm thinking, like earlier on, we were looking at different compositions with, so like here I was looking at the composition with Q, but you could do the same thing with H or V. Actually, David, to come back to your question, there might be something to the fact that we have double cat V there. So H and V interact slightly differently with things. But I guess if you were going the other way, then you would have to also switch that H and V there, the double functors. I think that's one place where, but the fact that you're working with double cat V, you have that affects things. so I'm now thinking, so let me just make sure I get the question right. For we just, oh, come on, aren't you nice to me? Are you now giving me, yeah, good. Need to convince the program to give you an extra page. And okay, so let's see. So we have a functor A, sorry, category A, functor. So were we thinking of going into cat first of all? Or
I was just thinking if we have a functor from A into double cat.
oh, into double cat itself already.
Like,
Okay.
are we able to recover, like, say, the square-shaped lax colimits from your construction somehow?
Okay, so if we go from A into double cat, so that means for every object we get a double category, for every arrow we get a double functor, and so we have, let's just call this one F. So F, let's call FA, FB, and so those are double categories. Here's a functor, and we don't have any cells right now. So let's see. So if we now, so i.e. just identities, and so if we do the, okay, good. So the question is now, if we want to do our construction, we have to decide how we are going to see A as a double category. Maybe that was your question to start with. I'm kind of together trying to figure out what the question is exactly, but so because I can see this, of course, as a functor from QA to double cats, and then I can do the construction. I can also see it as a functor from VA to double cats, and I can see it as a functor from HA to double cats. And just by the calculations I just did, I know that if I interpret it as this one, then I get the ordinary Lax Colimit, because it's a special case of the two. Well, I hope. I think so. If you take the Lax Colimit of a category, it's the same as the Lax tricolimit of interpreted as a two category. That's kind of the question, perhaps. I think it is, but I should check that. I think that everything that can be relaxed becomes identity automatically, but not 100% certain. The HA, would that, I'm not certain, Martin, if you help me think, would that be giving me the elements construction from Bob?
It might, but I'm still having a hard time understanding in the question, like, what do you mean random by that limit? Because when you think of it as a functor, then you have, if you wanna think of a two limit, then you have to give double cat a two category structure, and you have to make a place there.
So what you can make a double cat V, because it doesn't really matter because F doesn't hit it, so to say, but indeed you have to give it some structure, but I think it's harmless to go for the V. And then and then you need to still do indeed. So let's see, so we have, when I just take A as a category, then so we can see it as a double category VA, then I get, so we have, and I think you still have, once you do that, you still have your induced functor into double cat V. Still going to the same object, same double functors. And then you need to take the Q of that. To end up in Q double cat V. Wait.
I'm not sure.
No, no, sorry, we don't need the V. Sorry, this was without the V. Yeah, so this already needs to land. Wait a sec. Okay, sorry about that. Thinking our feet sometimes goes well and sometimes it doesn't. So I'm looking here for a moment. If I want a double functor, then I have to call it Q double cat V, and otherwise you have to call it a vertical functor. And yeah, so this is fine. You just have only vertical arrows. So basically this is factoring through V of double cat V, but doesn't matter. So I guess the only question is, okay, so what kind of limits do we get if we, so we can assume, so we can either go for VA and taking the induced F, or you can go for QA. So with V, I'm fairly certain you get the ordinary colimits, lax colimits. It's Q. I'm not sure. It might not add anything, but I'm not certain about that. And if you do H, then I think you end up with the elements.
Well, I admire your bravery, Dorette, to.
Well, this is half guessing. So I'll be honest.
Yeah, well, even to, and must have been a very good question, Brandon. So
I like it.
We like to stop around this time. If you I'm happy if you want to kind of wrap up what you were saying, or if you can. But we could also just end the live stream and keep talking. It's up to you.
I'm fine either way.
And Brandon, did you get what you wanted out of that, or?
Yes.
Okay.
Totally.
All right. Well, why don't we thank Dorette again, and okay, let's do that.